All right, everybody, welcome to another week of this wonderful course. Today we're going to talk about the t distribution. Earlier I mentioned when we discussed the normal distribution that the t distribution is related to it. In fact, the t distribution converges in probability to the standard normal distribution when the sample size gets large enough. So here's an example where we have the sample size. Basically, when we talk about degrees of freedom, it's the sample size minus one. So it's essentially the sample size. As the sample size increases, so here's with one, so this is two individuals, 1 degree of freedom, etc., and going on till we get to the standard normal. You see with the sample size increases, the two distributions converge. What's different though is that the tails are wider in the t distribution than in the normal distribution. We also call this the student's t distribution. I forgot who's it named after. Oh, geez, I can't remember. But anyway, the statistician, his bosses wouldn't allow them to use their name in publication, so he took on the pseudonym student, which is really interesting in my view. Hi, I'm student. My name is Daniel Student, and this is my distribution. All right, so we use the t distribution generally when we don't have information about the population standard deviation. The z-tests that we used previously, we could do this because we had information about the population mean and population standard deviation, but often we don't have it. This actually provides a great deal of flexibility for us, and I love this test. Now, as I've shown before, the population variance is an unbiased estimate of the sample variance is an unbiased estimate of the population variance. So then for the S, here is the standard deviation because the variance is S squared. So this is an unbiased estimate of the population standard deviation. If you recall from our discussion on distributions and testing, we can calculate the standard error of the mean by dividing the standard deviation by the square root of the sample size, right? We talked about that before, but here you'll notice that instead of a sigma, which meant population standard deviation, we use the sample standard deviation because it's an unbiased estimate. So here we are. Let's go to an example of one sample t-test. Our null hypothesis is that the sample mean is equal to the population mean. And we have all these different alternative hypotheses depending on what we're looking at. Either our sample mean is greater than the population mean. This is a one-tailed option. We're only looking at one side of the distribution, right? We're saying that our sample mean is greater than. We're looking at the right side of the distribution. Or we could say the sample mean is less than the population mean. That's another one-tailed option. So I have it as one-tailed option 1, one-tailed option 2, because there's two different ones. Or, of course, our alternative hypothesis could be that the sample mean is not equal to the population mean. That's a two-tailed option. Two tails, because when I say it's not equal, that means that the sample mean could either be greater than the population mean, or the sample mean can be less. So if we're looking at less, we're going in this direction. If we're going to greater, we're looking in this direction, right? Because our sample mean is here, right? It's 0, standardized at 0. So we're making this comparison to that. Our test statistic is the one sample t-test. So we're going to have three different t-statistics here today, right? One sample t-test, the paired sample t-test, and the independent samples t-test. So with this test statistic, we take the sample. It looks exactly like the z-test, right? Except for there's two differences. One is that we use the sample standard deviation, and the other is that we have our degrees of freedom, and we need both of these. Okay. We need both of these. So here's an example from our textbook. Do Mount Daniel skiers ski locals only faster than Mount Biscuit skiers? So here's what we know. So this is again why I like it. I go to Mount Biscuit. I talk to this skier there. Perhaps he's a Yeti. I don't know. But by the way, where I work, there's this guy. I call him the Blue Mountain Yeti because he's always like flying around the mountain, no poles, twin tip skis, looks really cool. He's got this cool outfit, breaks through the line. He's a jerk of some sort, but he's kind of a legendary jerk. So I call him the Blue Mountain Yeti. So maybe I spoke to the Blue Mountain Yeti and he said, hey, if you're going to be a good skier, you got to ski locals only in 90 seconds or faster. Okay, so our question is, do our skiers from Mount Daniel ski locals only faster than the Mount Biscuit skiers, or at least what that guy claimed they would do? So here's our data. We have 22 skiers and we calculated their time down the run. It was 83.952 seconds with a standard deviation of 12.29 seconds. So, well, just on the surface, it looks like they did better, but we don't know if they're statistically better. So here's our null hypothesis. Our sample mean is equal to the population mean, right? So that means we're saying that our sample mean, this one is not any different from 90. I mean, obviously it is different physically, right? I mean, or you're looking at 83 is less than 90. I mean, I'm not dumb. I know that, but the question is this an accidental finding or is this a real finding? So that's what we're looking at. So my alternative hypothesis would be that the mean from my skiers would be faster than those from Mount Biscuit, all right? Or that 90-second. So we select an alpha of 0.05 for this test, and we're using a one-tailed critical value. Okay, it's one-tailed because, again, our alternative hypothesis is directional. One-tailed means it's directional. So what's our critical value? So to find the t critical value, we need the alpha and the degrees of freedom. So our degrees of freedom in general is going to be n minus 1. Generally, degrees of freedom are used when we make some estimate of a population parameter, like we do. We're using the sample variance as an estimate of the population variance. So that's where we lose 1 degree of freedom. So here's what okay, so we have our alpha 0.05, and this should say 21 degrees of freedom, not 20. Sorry, that's my mistake. 21 degrees of freedom. And so we go to our table in the back of the book, and this is the table B, right? T table. This one's a lot easier to use than the last table, right? The last table, you have to think about the halves and subtracting or adding or whatever you have to do with the because we only got half of the z of the standard normal distribution. So here I know I'm using an alpha of 0.05 and it's one tail. So these are my alphas here. Here's 0.05, all right? And it says one tailed, right? So if I wanted to do two tailed, I'd have to move here, right? So there's one tail, two tail, okay? So we're looking, so this, for those of you who are interested, 1 minus 0.95 is 0.05 for one tail, okay? All right, so let's go here and look down for 21 degrees of freedom. And here it is. These are the degrees of freedom. Find 21, and we look for where they intersect. And they intersect at 1.721. 1.721. Now, this is positive, right? But we know because of symmetry, we have an equal value on the negative side of the figure, right? So if we were looking at our sample being greater than the population mean, we'd have positive 1.721. But since we're looking at whether our sample is less than or not than the population mean, it would be negative 1.721. So we go back here and we have negative 1.725, excuse me. So our decision rules would be that we reject the null hypothesis if our calculated value is less than, no, really it needs to be further away from the mean than whatever our critical value is. So it might be hard to remember, well, it's less than in this case, but it's greater than the other case. Just think about it, the further away you are from the population mean, the less likely something's to occur by chance alone. So we just want to be further away. So that means more negative than 1.725. Or we could also reject the null if the p-value is less than 0.05. This applies more to when you use a computer to do your work, because you usually get output they don't usually give you the critical value, but what you get instead is a p-value. So, and then we'd do a confidence interval for this. The confidence interval for the t-test is very similar to the z-test, except for, of course, we use our t-value here. And again, it's alpha divided by 2 because the confidence interval surrounds the mean. So it's always going to look at both directions, right? Either below or above whatever your value is. And then we use the standard error just as we did before. So let's go ahead and do this. Today I'm going to show you a lot of work. Sorry about the shadow here, but yeah, I wouldn't be good at taking selfies, right? Because I'm not, you can see I'm not very good here. So, all right, so we have n equals 22. Our question was, do Mount Biscuit skiers ski faster? So our null is that they're equal to 90, because that's our population mean. And the alternative hypothesis that it's less than 90. So again, it's a one-tail test. Alpha 0.05. We found our critical value to be minus 1.721. Our test statistic is the one sample t-test. I always write all this stuff down. We should always write down our rejection rule. Now notice here, I'll say reject if the calculated value, but notice that I use the absolute values. I want to get rid of that negative sign. So generally when I teach this, and in person as well, I always say, let's just focus on the absolute value. The absolute value just removes the sign. If we remove the sign, it's easier, right? And then me saying, well, it's further away, just remove the sign. Reject if the absolute value of the calculated value is greater than or equal to the critical value. And I say greater than or equal. Some people don't like that I say the equal, but that's incorrect. The real correct way to do this is greater than or equal to the critical value. All right, so we got 83.952 minus 90. We got 12.29 as our sample standard deviation divided by the square root of 22. We get 22 is our sample size. We get minus 2.308. And so since the absolute value of minus 2.308 or 2.308 is greater than, in this case, 1.721, we'd reject the null hypothesis. So our skiers are faster. Yeah, of course they are, because I probably worked with them. In terms of our 95% confidence interval, so we get a 95% confidence interval because our alpha is 0.05. 1 minus 0.05 is 0.95 or 95%. With a mean plus or minus m. M is the margin of error, right? Margin of error is whatever this t cutoff value is. So it's degrees of freedom 1 minus alpha over 2. Divide times the standard error of the mean, right? And now we're using a two-tail value versus a one-tail value, right? So because it's a confidence interval, so we have to look at the two-tail option here. All these little windows make it hard for me to see stuff. Okay. Here we want alpha two-tail at 0.05. So I look for the 0.05 that says two tails, right? Okay, so you should, based on what we did last week, you should understand why this says 0.975 here, right? Because at the right end of the distribution, it's the upper 0.025 or 2.5%. And then in the lower end, it would also be the lower 2.5%. Together, they would equal 5%. So here we have two-tail 21 degrees of freedom. It's 2.080. Okay, so you have to change it in this case. Right, 2.080, and that's what we use right here. 2.080 times 2.620. It's the same standard error. So once you do the standard error here, you're okay. And we get our 95% confidence interval is 78.502 to 89.402. All done. Yes. Booyah. Piper is really happy about that. My parrot, if you don't know, that's who's making all the noises behind me. The beautiful noises. Drinking some good coffee here. Long day of work today. I'm doing this. I teach a in-person class, 12:30, and then I teach class tonight at 6 p.m. Long day for me. All right, so let's do a repeated measures design. So repeated measures design is when we have the same people being measured at 2 time points. And this is for paired sample t-test. I mean, you can have more than 2. You can have 1,000 repeated measures on an individual, which we do sometimes. But here we're looking at paired sample. It means there's 2 time points. So it could be any kind of example. For instance, pre and a post test. Pre-test, you do something and then get measured again post-test, like say some intervention. Or it could be like your one individual is trying two different drinks and trying to say which of the two is better, Coke or Pepsi or something like that. See, the key is it's the same individual. So we have a repeated measure design. So let's just say we're comparing means from time one to time two. So not much of a difference here. We're using actually the same test, which is why I like the paired sample in comparison to the one sample t-test. The only difference you'll see is this little triangle here. That's a delta. Delta means change, right? So the null hypothesis is the mean change from the sample is equal to the mean change from the population. The alternative hypothesis is the mean change from the sample is greater than, a mean change in the population, or it could be less than the mean change in the population. Again, we have the one-tail option. The alternative hypothesis is the mean change is not equal to the population mean change. So that's a two-tailed option. These tests are actually very useful because you actually save money. In research, we have to recruit participants and pay participants. And if I could tell you that I could do the work with half the amount of participants, so saving you half the money, you'd probably say, wow, I want to do that. So this would save you half the money because instead of having one group of individuals, say, drinking Coke and the other group drinking Pepsi, and we compare them to see which one is preferred, I could do it with the same individual. So I cut the sample size in half. All right, so here's our test statistic. So it's the exact same test statistic as we used for the one sample t-test. The only difference is now you see the deltas, right? So the mean difference in the sample minus the mean difference in the population, right? The standard deviation of the difference divided by the sample size of the difference, square root of the sample size of the difference. And again, degrees of freedom is n difference minus 1. Okay, let's do our textbook example. Yeah, so here I am again, working my sports psychology, fun stuff. I used to study sports psychology, and that's what I started as a professor of sports psychology. Does the My Ski program improve performance in a race? So, this is my intervention to help skiers do better. Participants have been compared before and after an intervention. Here's what we know. Well, okay, so when we're doing difference scores, generally we're looking at whether the mean difference, the population mean difference is 0. So a population mean difference of 0 would mean that the intervention had no effect, right? If it had no effect, it means you skied equally well before and after the intervention. So that's your typical thing when we're comparing pre and post. I mean, you could put any value in there, but generally it's going to be 0. We don't have the standard deviation of the difference. So this is the mean difference in times down some race course was 1.27 seconds in the My Ski group and with a standard deviation of 1.83 seconds, and there were 15 individuals. So I'm going to use a two-tailed hypothesis here. I find it kind of difficult to track sometimes the difference, which is positive and negative when we're looking at a different score. So I'll just use the two-tailed option here. So my null hypothesis is that the sample mean difference is equal to the population mean difference. My alternative hypothesis is that there is a difference, but I don't say in which direction, so therefore it's two-tailed, right? That's the only difference here is I didn't say what it is. So that's how we get to the two-tail. My alpha, in this case, I'm using 0.10. My selection of alpha depends on the situation. It's very situational. I have only 15 participants here. We're not like curing cancer with a new drug here, right? So I can have an alpha that's larger than 0.05. There's no risk, in other words, from this intervention. If there was a risk, like I said, the way you're going to ski faster is to ski upside down, then maybe I would make my alpha 0.01, but I'm not doing that. Because our two-tailed critical values, we have our degrees of freedom is n minus 1, 15 minus 1 is 14. So we have an alpha of 0.10 two-tailed. So let's go over here. 0.10, alpha of 0.10. Well, it's right here, two-tailed. This is cool, though. So see how these match up, the one-tail 0.05 and the two-tail 0.10, because the one-tail only looks at the upper or lower 5% of the distribution. A two-tail looks at both 5%, right? So it's going to have the same cutoff. Is that wild? So the cutoff here is going to be for 14 degrees of freedom is 1.761. Here's my degrees of freedom, it's 14. So we go up here. Oh, I'm sorry, where were we? 1.761. Okay. So our rule is to reject the null hypothesis if the calculated p-value is further from the mean than either 1.761 or negative 1.761. Either, it doesn't really matter, right? It's two-tail. And reject. So, right. So again, we could just use the absolute values here. And again, we could use the p-value criterion if we had a p-value, but we don't have any p-values here. All right, so let's go to the highlights here. So this should be the next one. Hopefully this is all going to work out. Yes. My ski within. Let's see if we can get, yeah. So here we have our difference is 1.27. Our standard deviation of the difference is 1.83. Our sample size is 15. And we have our null is that the mean difference is equal to the population mean difference, the one that we observed, our sample mean. And our alternative is that they're not equal. We already did all this. We calculated our critical value to be 1.761. We just plug everything into the equation, right? Notice that the mean difference for the population is 0, right? As I stated before, that we believe the mean difference will be 0 because if the program doesn't work, it'll have no effect on skiing. So generally, you can just look at the mean difference in general, unless you have a very specific value that you want here. But generally, people use 0. 1.27 divided by the standard error, we get 2.688. Since 2.688 is greater than 1.761, we would reject the null hypothesis. I can actually find the p-value for 2.688. 2.688. Here, let's go down this column. 2.688. 2.688. Here, right here. Somewhere between here and here. So 14 degrees of freedom, 2.624 and 2.977. And we say it's somewhere between 0.02 and 0.01. But you generally don't have to do that because you'll have a computer do that for you, okay? So you can actually provide the p-value for that. Let's see if did I do the confidence interval? I didn't do the confidence interval for this. Here you have a couple of practice problems that you can work through. I'm going to provide you with all this information here so you can look at it for those practice problems. So let's go back here. There's 2 practice problems that you can work out. Okay, let's go to 2 independent means, comparing 2 independent means. Independent samples t-test. So now we're comparing 2 unrelated groups. So the last test, we compared the same individuals. I mentioned that. Often, though, we have different groups of individuals. We may be, for instance, and this one wouldn't be a really good experimental design, but for various reasons. But for right now, we're just going to use it as an example. We may be comparing, say, anxiety between people who are taking a sugar pill and people who are taking my famous sunshine pills, right? My famous drug, it cures everything. Or maybe we'll comparing a new treatment for math anxiety versus a standard treatment, right? Like maybe there's some kind of a intervention of so, or say we could be comparing 2 groups of individuals, like males versus females, on something like depressive symptoms. So we're comparing 2 independent samples. It means they're not related. There's no brothers and sisters, no twins or anything like that. They're 2 groups unrelated. So we use an independent samples t-test. Let's go through how we would do this, and I'll introduce everything you need to know. Excuse me. So you always state your research question first. So is there a difference in the means between our 2 groups? We write out our hypotheses, our null hypothesis. Now notice how I use mu here for each of these. That means I'm considering because we're not interested in whether, say, males and females different in our sample. We're interested in population differences between males and females, or between a population of people who take a placebo versus a population of people that take sunshine pills. Our alternative hypothesis is that well, we have two-tailed and one-tailed. Either our sample means are equal, that's two-tailed, are not equal, that's two-tailed, right? We're not saying the direction. Or we could do one-tail, like one group is less than the other. Okay, so those are two different alternative options. Right? Yep. Notice also here that I use HA instead of H1. So you can do either H1 or HA for alternative hypotheses. Whatever you want, that's fine. The appropriate test here, we'll have two independent samples. That's our independent samples t-test. We have to make sure that, well, we should be doing this for all of our tests. We have to make sure that our data meet our test assumptions. Our two samples are independent, that's one, and both samples are normally distributed. So you can look at the histograms to see if they look like a bell. If they do, that's pretty good. You can also look at skewness and kurtosis. Skewness means that you have some values that are outliers in one direction. So the distribution has a longer tail in one end. Kurtosis looks at whether it's flat or fat or whatever you want to say, thicker or flatter and taller in distribution. Got to define our alpha, whatever we want it to be. We find our critical value. So we're going to be doing similar to what we did before for finding our critical value, except for now it's a little bit different because we don't have a simple way to identify the alpha. And now this is where I may diverge from other professors that teach this course. Most people will teach the t-test that assumes that we have equality of variance. So I'm not going to do this. I'm going to use the test that does not assume equality of variance. So these two are going to be different in the denominator here. So they're different. Either we assume equality of variance or we cannot assume equality of variance. But to assume equality of variance, we should test for it. When you're doing this on a computer, it's really easy to do. If you're not doing it on a computer, well, then it's a little bit difficult. And more difficult. It's not horribly difficult. It's more difficult to do. So we're going to use the more robust test. It means it's better even if you have a violation of equality of variance when we do not assume equality of variance. Or it'll work as well if you have equality of variance. It's better than assuming that we have equality of variance, okay? So we're going to use this test. But to identify our degrees of freedom, we're going to use what's called a conservative method, where we look at the lower of the two groups' degrees of freedom. So we're going to look at n-1 in each group, right? N-1 in each group, and whichever is lower, that'll be our degrees of freedom. There is another way to do this, right? Welch's degrees of freedom, but that's a little bit more complicated to do. I don't know if I show you that here or not. I do in the book. I could use that as I'll give it to you as an extra credit problem during the exams. And you can just do that for extra credit because it's a little bit more complicated. It's in the book. It's explained. That's all you need to know. But you got to show me all the work, of course. All right, so find our critical value. And we always write down this rule. I say it's better to just write down the rule. Reject if the absolute value of the calculated value is greater than or equal to the absolute value of the critical value. Use your equation. And then write your conclusion, either reject or fail to reject, and provide a confidence interval. Now, confidence interval here, I'm going to just probably not do that for you because you'd really want to use the correct degrees of freedom here. That means you'd have to do Welch's test. So we'll just let you do that when you have a computer to do it, okay? Let's use a textbook example here. So we're working on the my ski problem again, but now we're using two separate groups of individuals. So we had 30 participants were randomly assigned to either my ski program or the traditional coaching problem, 15 per group. Here's what we know. We start with the assumption that there's no difference between the two groups, right? So it's 0. And so we have data. We have the my ski group completed this course, probably giant slalom course or something like that. Yeah, racing, 40.79 with a standard deviation 0.941 seconds. And the regular group was a little slower, 42 seconds with a standard deviation of 1.748. So we'll do it by hand. So I did it already. Now make sure I can find it for you. Let's go. So this is this is practice problems, I guess. Yeah, here we are. Okay. All right, so we write down our hypotheses. My ski group is equal to the mean for them is equal to the mean for regular coaching, and then my alternative is that we're faster. Now, choosing that alternative hypothesis, you look at the results. That if I give you the results in advance, like for instance, the my ski group was lower than the regular coaching group. We saw that it's lower. So why would we do anything but an alternative hypothesis that says the my ski group is lower than traditional coaching? It makes sense to do that, right? You get more power when you do a one tail versus two tail. So if you can do a one tail, it's better. So that's the way I look at it. Sometimes you can't do that, like you don't really know. So then you do the two tail. We used independent samples t-test. I'm not going to worry about, you know, there's some situations where we can calculate, we can use things like SPSS or a computer package to give us the information we need, like testing for equality of variance and stuff like that. But again, we're using this specific test. Here, our alpha, we're going to use 0.10 because we have a small sample. And again, this isn't anything dangerous to do. So our critical value, so we're going to look at the sample sizes. So we had 15 per group, so they're equal. So we're going to use a degrees of freedom of 14. Like if it was 13 in one group and 14 in the other, it would be the smaller of the two. So 13 minus 1 would be 12, and 14 minus 1 would be 13. So we take the 12, right? So we're going to take whichever is smaller. But in this instance, both groups have 15 in them. So 15 minus 1 is 14, right? So we'll go look at that up in the back of the book, and we're using a one-tail test, right? One-tail critical value, alpha of 0.10. Here it is one tail, right? 14 degrees of freedom. We get 1.345. 1.345. Sounds kind of funny. 1.345. There it is. All right. Calculate the test statistics. So doing this, you just have to basically follow all the rules here, but just remember that this is a variance down here. So it's squared, right? So in a test, I'll probably give you the standard deviation. You just have to remember to square it to get the variance. And I think a lot of students mess up on that, right? Take the square root of all that, and we get minus 2.3549, right? Minus 2.3549. So we're going to take the absolute value of that. The absolute value of this is 2.3549. Our critical value was actually was negative 1.345 because we're looking at us being faster. But again, I did the absolute value to get rid of that confusion. I just want to get rid of all that confusion. So the absolute value of negative 2.34549 is greater than the absolute value of 1 minus 1.345. So we would reject the null hypothesis. In other words, my skiers did better, of course, because I came up with that program. Of course they did better. Just kidding. And again, you have practice problems here you can look at. Some fun stuff to do. A lot of fun stuff to do. All right, let's move to the next topic. Next topic is analysis of variance. So analysis of variance, also known as ANOVA, is used when we compare more than two means, right? So greater than or equal to three groups. We can do that in different ways. One would be, say, if we're comparing three groups for a drug, like we could have high dosage sunshine pills, medium dosage sunshine pills versus placebo. That's three different groups, right? So when we do that, we would use a one-way ANOVA. Now, we can also have repeated measures ANOVA. I don't talk about that in this course here. I do it in a more advanced course if you're interested. And it's in the book. If you want, you can read it in the book. It's in the, and I think, I don't know if it's chapter 15 or what is it, but there's one on longitudinal designs. I saved it for that. I'm going to pause for a second. I'll be right back. And then we'll continue ANOVA is what's known as an omnibus test. So what we look at here is whether there's a difference among the groups, but we don't ask like where specifically is the difference. And if you know anything about life in general, they always want more information, right? So if I have three groups, like I said, two different doses of sunshine pills and the placebo, people would be interested in knowing which of the groups differ from the placebo, or does high dosage differ from low dosage? So that they're not interested in just the results of that omnibus test. So they'll start asking you to do more tests, like do these t tests within, right? Well, here's the problem. If we do too many t-tests, we increase the risk of what we call family-wise error. In other words, we increase our alpha. So alpha is the family-wise error rate. For if we do more than one test, the alpha we chose doesn't apply anymore. The alpha is for one test only. If we start doing multiple tests, then we have to basically lower our alpha per test. And I'll show you how that works. But first, let's start by looking at the impact of doing multiple tests. So to identify the impact, we're going to use the coefficient from our binomial. So we did the binomial earlier when we looked at distribution, so that we use the binomial coefficient here. Except for in the denominator, we're going to let x equal 2. And n is the number of groups there are, okay? So the question is, how many ways can we arrange two things and things two at a time, right? How many pairwise comparisons can we make out of n different groups? Okay. All right. So let's see. We already know how to do this, so I'm not going to show you how to do this again. Okay. But why the family-wise error rate? So the family-wise error rate equation is 1 minus alpha raised to the nth power, where n is the number of tests conducted, right? So n is the number of tests conducted. So if we say do our binomial coefficient and we come up with a certain number of tests, like say we can make 6 pairwise comparisons, so n then would equal 6. Okay. Well, anyway, let's look at this equation, why it works out and why it gives us the probability, why it gives us the family-wise error rate. So family-wise error rate is the probability of making at least one false positive. So at least one, it's a probability of at least one type 1 error. Type 1 error is a false positive result. If you remember, we had alpha is equal to type 1 error. Type 1 error means you have a false positive result. So we reject the null hypothesis when we shouldn't have rejected the null hypothesis. So if we do n tests, what's the probability that we get at least one false positive? So we rely on what we know about probabilities, and that's why we do this. So 1 minus alpha is confidence, right? Remember that we learned that earlier. Okay, so this is also not making a false positive, right? If alpha is the probability of a false positive result, 1 minus alpha is the probability of not making a false positive result. So we do it n times. So what we're saying is, what's the probability that we do not have a false positive or no type 1 error in the first instance? Here, right? And means multiplication, and the second instant, and the third instance, and the fourth, all the way till the nth instance, right? So this is the probability of no false positive results in all of those trials. Well, the probability of making at least one would be the complement of making none. So that's where we get the 1 minus alpha, okay? That's wild, huh? Yeah. Let's see if I have hopefully I have this demo here. Let's see. I should. Ah, here it is. Okay. So here's just for your FYI, for your information. This is the calculation of the number of pairwise comparisons we could make if we had 4 car brands. So n equals 4 and x equals 2 here because we're doing pairwise comparisons. So it'd be 4 choose 2, 4 minus 2 because n minus x is 2. Right? If you should remember this because we did this earlier, that would give us 6. So if we have 4 cars and we want to compare like the 2 different cars on, say, customer satisfaction among the different brands, we can make 6 comparisons. The question that we just did now, we wanted to know what's the family-wise error rate if we make all possible comparison among 5 different things, right? Let me just go back and see what the exact question I had was here. What's the family-wise error rate for making all pairwise comparison a study comparing 5 groups with an alpha of 0.05? So let's go take a look at that. So we have n equals 5 in this case. Of course, x is 2 because all pairwise comparisons. We use the binomial coefficient again here. It's 5 factorial divided by 2 factorial times 3 factorial. 5 minus 2 is 3. 3 factorial. Do a little canceling out here. So we get 5 times 4 is 20 divided by 2 is 10. So we can make 10 possible pairwise comparisons. So what happens if we do 10 pairwise comparisons? We use our family-wise error rate equation. That's a probability of at least 1 false positive, 1 type 1 error for alpha 0.05. And the number of comparisons we can make is 10. So notice here, just to keep track of things, the n here is different from the n here. The n here is the number of the groups you have, where you're making x is the number of pairwise. X is 2 because it's a pairwise comparison, right? The n here is the number of comparisons you could make. So you take the result from the first calculation using the binomial coefficient and plug it into the n here. Okay, so those are 2 different n's. You got to keep track of this stuff. So 1 minus 0.095 raised to the 10th power, we get 1 minus 0.599. And look at this, we've increased our probability of a false positive result from 0.05 to 0.40. So we've had a drastic increase in our probability of a type 1 error by making this many pairwise comparisons. Okay. Let me see if I'll just keep on going down. I think I talk about it later. All right, so there's some assumptions for ANOVA. And the assumptions are that we have equality of variance. So that's an assumption, just like we had for t-test, but I said we skirted that issue because we use a different equation, but here we're not going to skirt that issue. We have normality at each level of the independent variable, the grouping variable. The independent variable is the grouping variable. Like for instance, by saying the 2 different doses of sunshine pills and placebo, that's my independent variable. That's a grouping variable, the dosages and the placebo. So if we're looking at high dose, low dose, placebo, I'd expect to have normality in each of those levels. And the observations are independent, so they're not paired or grouped together in some way. So it's not like brother and sister or me doing 3 different dosages, right? Doses, excuse me, of sunshine pills. The ANOVA is calculated as follows. It uses the distribution called the F distribution, right? The F distribution. And this F distribution uses this ratio right here, or yeah, the ratio of the mean square between to the mean square within. We're going to go over all that, so I'm not going to leave you hanging here. Let's talk about what this is. Okay, so I just started by giving you the equation. This is our test statistic, but let's go back and diagnose this or break it down into different parts. First of all, well, when we partition variance, we're looking at the variability in our dependent variable, whatever our dependent variable is. Like say we're looking at the different dosages of this drug, how it affects depression, because we have all these people and they have different scores on depression. So we want to look at how much variability there is in depression. So that's the total variability. Now notice how I say sum of squares here versus variance. Sum of squares is actually the numerator of our variance equation. Okay. So it's a sum of squares. So it's a sum of squared differences. That's what we mean by sum of squares. So we can break down the sum of squares into the sum of squares between and the sum of squares within. The between sum of squares is the sum of squares that's partition among those three different groups, or how many groups we have, right? The within sum of squares is individual differences within an individual. So, but that's not of interest to us here. We're not looking at repeated measures designs. We're looking at the same person. We're interested in whether we can explain the variability that we see based on differences among the groups. So the means of the different groups will be different. Okay. Sum of squares total is the sum of squares between and sum of squares within. So if you have two of the three of these, you can calculate the other, right? If I know these two, I can get sum of squares total. If I know sum of squares total and sum of squares between, I can get sum of squares within. All right, so this is an example of the sum of squares total. So this is the equation for what we call the grand mean, or the grand variance, right? The grand variance. The variance, when I say grand variance, I'm talking about the total variability, ignoring the different groups. So if I forgot that there are different groups here and I just wanted to calculate the variability, that would be my grand variance. So my sum of squares total is each individual score on whatever my dependent variable is minus the grand mean, right, squared. So this is the numerator of an equation. But here's the interesting part. If I know the variance, the total variance, the grand variance, I can easily calculate this equation, this sum of squares total, because we know it's the numerator of my equation. All I have to do is rearrange the variance equation, right? I multiply each side by the denominator of the variance equation. So if you're not remembering that, you need to go back and look at the variance equation, right? I'm sure I show it in the book. So I multiply both sides by n minus 1, right? So what would be left would be sum of squares total is equal to the grand variance times n total minus 1, right? So it's easy for me to calculate the sum of squares total if I have the variance. For sum of squares between, it's the sample size for each group times the difference between the mean of the group and the grand mean. So we're looking at how much difference, this is what really determines whether we have statistical significance or not, is the difference between each group mean and the overall mean large. That's what we want to see, right? So we're trying to explain what the variability we see based on this difference in means. So to calculate the sum of squares between, we need to sum from I equals 1 to k. Now we're summing across the different groups. K equals the number of groups. So if I have three groups, like high dose, medium dose, high dose, low dose, and placebo, that's k equal to 3. So I'd have to do this 3 times. For high dose, I'd look at the sample size in the high dose group, take its mean minus the grand mean squared, right? Then I'd add to that the same calculation for the low dose, and then I'd add to that the same calculation for placebo, okay? My degrees of freedom here is the number of groups minus 1. So if I have 3 groups, it'd be 3 minus 1 is equal to 2. Oh, yeah, here's the variance equation. So you can see that the numerator is the same as this. Then finally, we have the sum of squares within. So in this case, the sum of squares within, well, for each group, we're just using the numerator. So if you have the variances for each group, you can easily solve this. Listen, in this course, I don't make you calculate this, so I'm just showing you how it's done. But you do need to know how to find the F statistic if I give you all the information. But you're not going to need to know how to calculate this, but I'm just giving you the information. So we do this for each of the 3 groups. Again, k is equal 3 if we have 3 groups. So for each group, we're going to calculate the difference between each individual score and the group mean. Okay. The degrees of freedom here is the difference between n, the total sample size, and the number of groups. So it's n minus k. All right. So to calculate, and also the degrees of freedom total equals the degrees of freedom within plus the degrees of freedom between, just like the sum of squares total equals the sum of squares between plus the sum of squares within. So if we went back here and looked at our F statistic, it was mean square between divided by mean squares within. So here's mean squares within. That's sum of squares within divided by degrees of freedom within. So it's like an average sum of squares, right? Mean square between is sum of squares between divided by degrees of freedom between. And then here's our F statistic. Voila. Try to see if I think I did this one all here. That's cool. Good for you. All right, so imagine that I'm conducting a study to determine which Philadelphia professional sports team. For those of you who are not from Philadelphia, we have teams here as well as all cities. Which professional sport team causes their fans the most stress? From among the four major sports, you have the Sixers, the Eagles, the Phillies, or the Flyers. I measured stress. This is, of course, a fictitious example. I measured stress with the 10-point Liberty Bell fan stress scale, LBFSS. Possible scores range from 0 to 50. I collected data from 100 random Philadelphia fans, 25 from each of the four sports. Table 1 includes the results of this study. Well, that's a lot of people. Right there, here's the results, right? Null hypothesis. So this, again, it's an omnibus test. So there's four groups. There's four group means of stress. So our null is that the mean in group 1 is equal to the mean in group 2, is equal to the mean in group 3, is equal to the mean in group 4. The alternative is that at least two of the means are not equal, right? So again, it's an omnibus test. It doesn't tell us which groups, but it says at least two of them are not equal. We select an alpha of 0.05. So we need to find our degrees of freedom here. I got not degrees of freedom. I'm sorry. Our test critical value, right? So we have 100 individuals. Our degrees of number of groups is 4. So if we look at our degrees of freedom total, where is that here? N minus 1, right? N minus 1. Let me find where we are here. Okay. Okay. How many people did I say? We have 100 random Philadelphians. Okay. All right, so where's our table? Our F table. So we don't have our actual value here. We don't have our actual value here. Oh, the degrees of freedom we're looking at here. Let me stop 1 second here. I have to pause this for a second. Sorry. Okay, so fortunately for you, I gave you an easier table here. So in this table, we're just using alpha equals 0.05. Most of the time when you do an ANOVA, you're going to be using it on the computer. But here, the way we read this table is we need the numerator degrees of freedom and the denominator degrees of freedom. So let's go back here for a second. So we have 4 different groups. So our numerator here is the mean squares between, right? For the F, it's mean squares between divided by mean squares within. So we need the degrees of freedom for the between sum of squares, and then we need the degrees of freedom for the within sum of squares. The degrees of freedom for the between sum of squares is 3, because it's the number of groups I have. 4 minus 1 is 3. So that's why I have F3, and then I have 96. 96 is for the within group. So the within group, we had to do n minus k. So n was the sample size, 100, minus the number of groups, which is 1, 2, 3, 4. So that's where we got 100 minus 4 is 96. So that's where we get 3 and 96. We need to look for an F of 3, 96. Now, we don't have that many values here. So we only go down to 60 and then 120. So I mean, I don't have 96 here, right? For the within, right? So I'm going to use the larger critical value, right? The larger critical value. So here we have 3 for the numerator, and then for the denominator, I'm going to pick the larger. So 2.68 is smaller than 2.76, so it would be easier for me to reject the null hypothesis at 2.68 than it would be at 2.76. So I'll take the more conservative value just to, to show that I mean business here. I don't want to, make it easier for me to reject the null. I want to make sure that what I have is statistically significant. Okay, so I chose that value of 2.76 as my critical value. Notice that I have the little squiggly tilde thing on top of the equal, so that means approximately. So let's go ahead and calculate our, geez, where am I? Our test statistic value. So first of all, we have sum of squares between is equal to sum of squares total minus sum of squares within. So I have values already. I have you'd have to actually calculate these, right? But I would give you these, right? So I'd give you values like this, sum of squares total, sum of squares within. So you'd have the value, and then obviously the between, well, we could easily find that by subtracting 5,200 from 83,325, because we know that these two added together equal the total. So we just rearrange our equation there, right? So subtracting the within from the total, we get the between value, 78,125. Then we can just go ahead and do our calculation. So this is the between, mean square is between, we divide by its degrees of freedom. Mean square within, we divide by its degrees of freedom. And then our F statistic is 480.769, which is much larger than 2.76. So we clearly reject the null hypothesis. So we know there is a difference among the means. All right, so we know that there's different, we just don't know where that difference is, right? But we can reject it. Okay, so in doing a real analysis, we start saying, okay, where is this difference? But because of what we know about family-wise error rate, in order to adjust for that difference, we will use what's called a Bonferroni correction. Although there are other types of corrections as well. We'd use a Bonferroni. It's a very conservative one. What we do is we divide our alpha by the number of tests we could do, right? So remember, we calculated the number of possible tests in an example where we had 5 groups or something like that. I think we did that. What do we say? There were 10 different tests you could do with 5 groups. Here. Yeah. I think we did that here, right? How many pairwise comparisons? 5 groups, right? We did that, and we found that we could do 10 different comparisons. So what I would do in order to maintain an overall alpha of 0.05, I would just take 0.05 and divide it by 10, and that would equal 0.005. So for each specific test comparison, my alpha would change to 0.05. That means to reject the null, I'd have to have a probability value less than or equal to 0.05. So that's what we do in order to deal with doing too many comparisons. We look for a smaller and smaller, make an adjustment to our alpha. However, there are other ways to do this. Here, well, let me just get rid of that. There are other ways to adjust for these differences when you're using a computer package. The computer package will offer you different options. One of them is called Tukey's honestly significant difference. So this would be an option other than using the Bonferroni, right? So it's a different choice. There's also Gabriel's and Hochberg's G2 squared, and then there's Games-Howell. They depend on which assumptions are violated, or if any assumptions are violated. If you have equal sample sizes and equal variances, you could use this Tukey's honestly significant difference. So it'll spit out, the computer package will spit out the results, and you'll determine whether it's statistically significant, but it'll adjust them for multiple comparisons using Tukey's honestly significant difference. We could also use, if we don't have equal sample sizes, we could use either of these two. If our variances are not equal, we could use this Games and Howell's test. So those are just different ways that we could do post hoc comparisons. But the easiest one to do, especially if you're working by hand, is to use a Bonferroni correction. We also like to provide effect sizes. Effect sizes tell us if two groups are different and if they're meaningfully different. When we do statistical significance tests, we just know that two groups would be significantly different, but just because two things are significantly different from a statistical sense doesn't mean that they're meaningfully different. To provide a measure of meaningfulness, we have to create some kind of an effect size. This one is called the eta. So this symbol here is eta, ETA, eta. This is called an eta squared. It looks at the sum of square of the effect. In this case, the effect would be the between, sum of squares between, because that's what we're testing, right? Divided by the sum of square total. So it gives us some kind of a value, or some kind of a proportion, right? Basically, it's telling us what proportion of the total sum of squares is accounted for by our treatment. There are heuristics for this. There's small, medium, and large different effects, small, medium, and large effects. So if I have my eta squared is around a little bit above 0.01 to less than 0.06, I'd consider it a small effect. If it's between 0.06 and 0.14, I'd consider it a medium effect. If it's greater than 0.14, it's a large effect. All right, so this is stuff that you need to know in relation to doing testing using ANOVA. On an exam, I'll most likely give you information like I gave in this table here, right? And have you calculate everything. I'd ask you how to calculate the probability of at least one false positive result, family-wise error rate. I'd ask you to calculate the number of comparisons you can do. I'm not going to ask you to actually, calculate sum of squares because this is not necessary, right? And then I'll likely ask you how to, like, if I give you a scenario, what type of post hoc test should you do? Or maybe even how to calculate the Bonferroni. How would you do that? But I'm not going to give you things that we're not covering in this course, okay? That's all I have for today. Thank you very much, everybody. It was great time as usual. All right, bye.